right? Now, in the abstract, I'd like to calculate what happens with d mu dx. You guys like mu, or do you like? My mu looks too much like a y. I'm gonna switch over to big I, if you guys don't mind. Sorry. Let's use big I instead. My mu looks too much like a y in here. Big I. I for integrating factor, okay? Sorry, you electrical engineers. I know you like to use I for something else, right? So di dx, what is di dx here? So by the chain rule, right? What's the derivative of the integral? I mean, so look at what we got. This is p, right? What's e to the integral? What's the thing out front? It's I again, right? So we have the following identity. di dx is equal to I times p. That identity will also be true for the one I specifically calculated for my problem. Next move. So just to tell you, you know, this was step number 1, identifying the problem. Step number 2, calculate the integrating factor. Step number 3 is multiply ODE by I. So that gives me, and I'm talking about the standard form one. So that gives me x squared dy dx plus 2xy equals to 3x squared. Right? For the generic one, it gives me I times dy dx plus IP y equals to IQ. Now, yeah. So can you guys tell me, what is this the derivative of? And it's also true in the abstract. This is, you know, d dx of what? Equals to IQ. And this is also step 4. So differentiate what to get 3x squared on the my specific problem? Y times what? Yeah, exactly, x squared times y. By the product rule, gives you x squared dy dx plus 2xy. This is just the product rule using implicit differentiation, right? But that's also true over here. In general, that will always happen, that this is IP. Right? Now how do we isolate y then? Just integrate both sides now, right? So step 5, integrate. We get x squared y is equal to x cubed plus a constant. Therefore, y is equal to x cubed plus a constant over x squared. Or if you like, x plus c over x squared. There you go. That's the solution to the differential equation using what is known as the quote-unquote integrating factor technique. The integrating factor technique is this 4 or 5 step process. Identify your problems in the linear differential equation, calculate the integrating factor, I, multiply by I, multiply by I, reverse product rule, and then you can integrate both sides to find the answer. See? So step 5 over on the general side, it says IP is equal to the integral of IQ dx. So, oh, is IP over here? Come on, guys. I what? I y. I y. So generally speaking, we find y is equal to 1 over the integrating factor integral of IQ dx. Now, I always try to emphasize, because some of you, there's always a student in here who understands this in the wrong way, which is, oh, you just found a formula. I can use it, right? The left-hand side's a formula. I just use the formula. No, that's the wrong approach. It's important to actually go through the derivation every time you do this. There's a couple of reasons. Well, the main reason is this. If you've calculated the integrating factor correctly, and you think going from step 3 to step 4, you'll be able to see if you made a mistake. Actually made a mistake up here, because if you made a mistake calculating I, this step won't actually make sense. But if you calculate the integrating factor correctly, then you'll be able to see the reverse product rule going from step 3 to step 4. So doing the calculation like this, as opposed to just reciting a formula, is much better because there's a redundancy in the calculation. There's a check on whether you're doing things right. But that's our 2 methods in here. We have separation of variables and we have integrating factor method and applied problems. That's pretty much it. So we'll look at more tomorrow. Sorry I didn't ask any homework questions today. We do have tomorrow though. So thanks guys. Oh, and we haven't top-headed. No. Did you have? Oh no, it's fine.